Hello everyone. Let's start a new chapter, chemical reaction. A chemical reaction is a process where one or more substances called reactant change into one or more new substances called products. Uh, Chemical reaction involves a change in composition or rearrangement of atoms within a molecule. Uh, Energy is always involved in a chemical reaction. Energy is always involved in a chemical reaction. A chemical reaction can either release energy or absorb energy, and based on whether a chemical reaction will release or absorb energy, it can be an exothermic reaction or endothermic reaction. A chemical reaction that releases energy is called exothermic reaction, and a chemical reaction that absorbs energy during the reaction is called endothermic reaction. A classic example of exothermic reaction is the combustion, and let's look at an example of a combustion of natural gas. The main composition of a natural gas is methane. When methane reacts with oxygen, it forms carbon dioxide gas plus water, and it releases heat. And if we were to write it in a chemical equation, we can see here methane reacts with oxygen and it produces carbon dioxide, water, and heat. And since the heat is a result of the chemical reaction, this chemical reaction is called exothermic reaction. Similarly, a classic example of endothermic reaction is melting a solid water or ice into a liquid water form. If we have a solid water and we add heat energy to the solid water, we will get a liquid water. And since the heat energy is needed to start the chemical reaction, we call it endothermic reaction. uh, Before we write chemical reactions, we must use language for our chemicals, uh, and we call this language of using element symbol to represent a chemical as a chemical formula. And this chemical formula represents the types and number of atoms in a compound. So this chemical formula represents type as well as number of atoms in a compound. And there are three main types of chemical formula: empirical formula, molecular formula, and structural formula. The empirical formula represents the simple whole number ratio of atoms of each element present in a compound. A molecular formula represents the actual number of atoms. This is a simplest whole number, this is actual number. And if we go even further, we have a structural formula, and this structural formula shows how atoms are arranged and bonded together in a molecule. We will talk about structural formula later in other chapters, and we will focus on empirical formula and molecular formula in this chapter. Let's look at the difference between empirical formula and molecular formula in more detail. As we defined, empirical formula is the simplest whole number, whereas a molecular formula is the actual number of atoms. And we can also see a better way to represent it here using this whole number n. So the molecular formula will be the n times the empirical formula. And we should also remember that this n integer will always, this n number will always be integer. Let's look at an example. We have a glucose. The molecular formula for glucose is C6H12O6. This is the actual molecular formula of glucose, and if we were to represent it in the empirical formula, this will be C2H2O, because this is the simplest ratio, uh, simplest whole number ratio of this molecule. And if you were to multiply this by this number and n, we will get the molecular formula, where this will be, if n equals to 6, this will be C6H12O6. Similarly, benzene is C6H6. The simplest whole number ratio is C and S, because both carbon and hydrogen are in equal ratio here, 6 and 6. So the simplest whole number ratio is 1 is to 1, and n is equals to 6. We can look at more example here, HO, H2O, and so on. And we should also note that in some cases, in some reaction where the integer n is 1, the empirical formula and molecular formula will be the same. For example, here we can look at the chemical formula for water. The empirical formula is H2O, and as we know, the chemical formula for the molecular formula for water is also H2O. The empirical formula and molecular formula is same, because this factor n is 1, and if we were to multiply the empirical formula by 1, we will get the same formula. A chemical reaction, uh, so we talked about chemical formula. Now a chemical equation is an expression that shows the formulas and the relative amounts of reactants and products, and the chemical equation visually represents the arrangement of atoms that occurs during the chemical reaction. So basically, a chemical equation is a way to represent the reactants and the product uh, involved and produced in the chemical reaction. As we defined in previous slide, the starting materials uh, are called reactant, and in a chemical equation, the reactants are always written on the left of this arrow. We can see here an example of chemical equation where we have a methane, oxygen, carbon dioxide, and water, and the reactants are written in the left side of the arrow, and the new substances called product are written on the right side of the arrow. And this arrow, when we are reading this chemical equation, this arrow is read as, sometimes you can call you will read it as else, sometimes you will also see produces. So methane and oxygen reacts to produce carbon dioxide and water molecules. And if we see here in the chemical formula and chemical equation, we can see some of these numerical numbers are written in written as a subscript here, and you will also see some some reaction with number in front of molecules. For example, let's look at a reaction here, the same reaction from here. we have methane reacts with oxygens to produce carbon dioxide and water. And if we look at here in these chemical formulas or the chemical equations, some of the numbers are in subscript, some of the numbers are in coefficient. And so as we can see, the number written in as a subscript or coefficients have different meaning. These subscripts are the small numbers that denote the number of atoms of each element within a single molecule. For example, uh, if we just take this H2O, we can say there are two molecules of hydrogen and two uh, atoms of hydrogen and one atom of oxygen within a water molecule. And the coefficients, the large number in front of this molecule, in front of the molecules, that denotes the number of molecules or formula units. For example, now oh, if we take this whole block here, what we see what this represents is basically two water molecules. So H2O was from this subscript, we know two hydrogen atoms and one oxygen atom. But if we were to look at this coefficient, what that represents is basically two water molecules. Similarly here, CS4 is methane. Methane is made up of one carbon dioxide atoms and four hydrogen atoms, and in this whole reaction there is only one molecule of methane, two molecule of oxygen, and a molecule of oxygen is made up of two atoms of oxygen. And this reaction produces one atom of carbon dioxide, and the carbon dioxide is made up of one carbon atoms and two oxygen atoms plus two molecules of water, and water is made up of two atoms of hydrogen and one atoms of oxygen. A central principle in chemistry is the law of conservation of mass. And the law of conservation of mass states that matter cannot be created or destroyed, but it can be uh, rearranged to form a uh, new matter. So basically, this law of conservation of mass is uh, preserved, or we can say the law of conservation of mass is followed or is obeyed within a chemical reaction, meaning the total number of atoms within the reactant should be equal to the number of atoms in the product, because uh, atoms can neither be created nor destroyed, but they can only be rearranged. Uh, what this means, the conservation of mass, what this means in term of chemical reaction is that the number of atoms for each element must be same in the reactant side and the product side. Uh, so what we do to achieve this conservation of mass is that we have to balance this chemical equation. For example, the same the reaction we saw before, uh, methane plus oxygen produces carbon dioxide and water. And if we just see this equation here, we can if we count this element individually, we have one carbon atoms in the reactant, four hydrogen atoms and two oxygen atoms. Basically one carbon atom, four hydrogen atom and two oxygen atom. And in the product side we have one carbon atom, two hydrogen atom and three oxygen atoms. And if we compare these atoms in reactant and product side, oxygen is balanced, but if we see here, we have four hydrogen in the reactant, but only two hydrogen in the product side. Similarly, two oxygen atoms in the reactant side and three oxygen atoms in the product side. If the chemical reaction follows the conservation of mass, the number of atoms in this side should be number of specific atoms of a specific element in this side should be equal to number of atoms of that specific element in other side. So in order to make so, we will balance this equation, and we can see here this balanced equation. And if we count this number of atoms here, we have one carbon atom, four hydrogen atom and 2 times 2. So basically how we will look at this is we will multiply this subscript to the coefficient of coefficient, and if we do so, we have four oxygen atoms in reacts as a reactant, and if we count this element in the product, we have one carbon. Again, 2 times 2 is 4 hydrogen atoms, and 2 times 1 is 2 times 1 is 2 plus O2. So we have total of 4 oxygen atoms, two oxygen atoms from carbon dioxide and 2 oxygen atoms from hydrogen molecule, water molecule. So the overall equation here is balanced. And in order to balance the equation, we have to assign this whole number. We have to assign these coefficients on these equations, not the subscript. Remember, we are not allowed to change the subscript because this represents the number of atoms within a molecule. Rather, we will only change the coefficient to to balance the equation. And here's step-by-step procedures for balancing a chemical equation. First, write the unbalanced equation, identify atoms that need balancing. Often it is easiest to start with the most complex molecule. When we have multiple molecules within a chemical reaction, it's easiest to start with the most complex molecule, and then we will adjust these coefficients through trial and error. And once you figure out a coefficient that will balance, we will confirm that. We will check the number of atoms in reactant sides and product side to make sure the chemical equation is balanced. And if needed, we can simplify the coefficient to be the smallest possible number. Let's look at the same example. We have hydrogen and oxygen reacting to create an water molecules. Now if we count here in the reactant, we have two hydrogen atoms, and if we look at a product, two hydrogen. So this is a reactant side, this is product side, two hydrogen, and if we look at oxygen, there is two oxygen in the product, but only one oxygen in the product side. So in order to make equal number of oxygen on both sides, what we have to do, we have to start playing with the coefficients on both sides to create an equal number of element in both sides. So if we look at here, we can see there's two hydrogen, two oxygen, and only one oxygen. That means we should at least put or make this oxygen atom, make this oxygen atom on the product side to be 2. So we can do that by multiplying by 2. Now if we count again, 2 hydrogen is still 2 hydrogen, but if you look at here in the product, we have now 4 hydrogen atom. And if we look at oxygen, 2 oxygen atoms, and here 2 oxygen atoms. So in order to solve that problem, if we put 2 here, now if we compare left side and right side, this is 2 times 2 4 hydrogen, 2 times 2 4 hydrogen, 2 oxygen, and 2 times 1 is 2 oxygen. So now our balanced equation is here, where 2H2 plus O2 produces 2 water molecules. So basically 2 hydrogen molecule plus 1 oxygen molecule produces 2 water molecule. So this is our balanced equation. A balanced equation provides information, the quantitative information about this chemical reaction. This chemical provides quantitative information about chemical equation, and this chemical equation shows the relative amounts of reactant and product. This chemical equation, as we talked about in the previous slide, has both a subscript and coefficient, and if we use this coefficient and subscript, we can calculate the relative amount of reactants and products. A chemical equation also uses this abbreviation for physical state of the material. S is for solid, L for liquid, G is for gas, and sometimes you will also see AQ. This is used for aqueous solution, which basically means dissolved in water. So if we see the previous example, we looked at creating where hydrogen and oxygen reacts to produce water molecule. We can see here hydrogen is in the gas form, oxygen is also in gas form, and the product of hydrogen gas and oxygen gas is liquid water. And like we said before, if we were to interpret this chemical equation, we can say 2 hydrogen atoms reacts with 1 oxygen atoms to produce 2 water molecules. Sorry, it's not atom. 2 hydrogen molecule reacts with 1 oxygen molecule to produce 2 water molecules. And we will also talk about these moles in next slide, but we can also have a quick look here. When we say this is 2H2 plus O2 plus 2H2O, this can also be interpreted as 2 moles of hydrogen reacts with 1 mole of oxygen, and this reaction produces 2 moles of water. All these chemical reactions can be typically classified into multiple categories. The first simplest form of chemical reaction is synthesis or combination, where two or more reactants form one product, and we can represent it in the form of A plus B produces A, B. So we have one reactant react with other reactant to get a combined product of some other element. This is an example of synthesis or combination where hydrogen and oxygen react to create uh, one element, one molecule, and that is water. Similarly, decomposition is basically the opposite of synthesis or combination, where one uh, one reactant is split into uh, two or more simpler substances. For example, if we look at here in this equation, mercury oxide, this Hg is mercury, the elemental symbol for mercury. So mercury oxide uh, produces mercury plus oxygen. So one reactant is split into two or more product. And then we have a single replacement, where one element replaces another element in a compound. For example, we can write this single replacement in the form of this equation, where this is reactant 1, reactant 2 results in product 1, product 2. If we see here, this is A reacts with BC, and then it produces AC plus B. Basically this A replaces B and form AC plus B. Let's look at an chemical reaction here. If we have the zinc and hydrochloric acid react, if a zinc and hydrochloric acid reacts, it will produce zinc chloride plus hydrogen gas. And if we see here, zinc will replace hydrogen from hydrochloric acid to from zinc chloride. And as we said from previous slide, this S here is for solid, L for liquid, G for gas, S for solid, and A is for aqueous, meaning HCl is dissolved in water. And this is the single replacement, where one of the element is replaced with other element. And there are more kind of reaction, where one of the example is a double replacement, also called ion exchange reaction. In this reaction, ions are exchanged between two compounds. For example, here this equation can be written in this form: A plus B, AB plus CD produces AD plus CB. Here if you see, AB is split and now it's combined with A and D, C and B, And if we were to look at an actual chemical reaction example, we can see here Ag is silver nitride in aqueous form plus sodium chloride in aqueous form will produce silver chloride plus sodium uh, nitride. And if we see here, uh, silver is replaced by sodium, and here sodium replaced by silver. And then the last type of chemical reaction is uh, reduction reaction, also called redox. And this reaction involves transfer of electrons between substances, and the substance that will uh, lose the electron is called oxidized, and the substance that will gain electron is called reduced, and thus the name oxidation and reduction. Here we can see an example: sodium plus chlorine reacts to create sodium chloride. And if we see here, sodium is oxidized to sodium ion and chlorine is reduced to chlorine ion. So this is oxidized and this is reduced. And the simple definition of oxidation and reduction is also listed here: undergoes or caused to undergo a chemical reaction in which electrons are lost, meaning there are more positive charges within an element resulting in positive ion. Similarly, for reduction, there are more electrons compared to protons resulting in negative ions. The molecular weight, also called formula mass, the molecular mass, this molecular weights also called molecular mass. Even though weight and mass are different, this term molecular weight or molecular mass are used interchangeably. And this molecular mass is the sum of the atomic masses of all atoms present in a molecule, and the unit of this molecular weight is atomic mass unit and written as AMU for in short form. And to calculate this molecular weight, you simply multiply each element's atomic mass by the number of its atoms, and then you will add the results. For example, if we were to calculate the molecular mass or molecular weight of water molecule, we can see there are 2 hydrogen atoms and 1 oxygen atom. So the total molecular mass will be 2 times the atomic mass of hydrogen is 1 plus oxygen is 16, so total of 18 atomic mass unit. Similarly, carbon dioxide, we have 1 carbon and 2 oxygen. The molecular atomic mass of carbon is 12, atomic mass of oxygen is 16, resulting in a total atomic mass of carbon dioxide as 44 atomic mass unit. Similarly, C2H12O6, if we were to calculate the molecular mass of glucose, this is glucose, molecular mass of glucose, we will have 6 times atomic mass of carbon 12 plus 12 times atomic mass of hydrogen plus 6 times atomic mass of oxygen, resulting in 180 atomic mass unit. To work with atoms, ions, or molecules, as we know, these are very very small. So the calculation uh, of these atoms, ion, or molecules are uh, it will be really complicated if we were to calculate one by one. So instead of doing so, uh, uh, a concept, this mole concept is used to do the calculations related to these atoms and molecules, and this unit is called a mole, and this mole is the SI unit. SI unit used to count particles, atoms, ions, or molecules. In some words, we can say this mole concept or one mole is similar to, we can call this mole as a chemist dozen, meaning uh, it's a fixed number. With if we have one mole of certain atoms, we will have some fixed number of particles within that one mole. Just like one dozen of a banana is like 12 bananas. Similarly, we have one mole of certain atoms will have 6.022 into 10 to the 23 number of that particles, and this number 6.022 into 10 to the 23 is called Avogadro's number. And this number is used to calculate this Avogadro's constant, also represented as Na, and we will use this Avogadro's constant later on to calculate the molar mass uh, 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 of an element, and this Avogadro's constant will have a unit of 6.022 into 10 to the 23 mole per mole. So Avogadro's number is this number of particles, and Avogadro's constant is Avogadro's numbers per mole. For example, let's see what this mole concept is in an example. For example, if we have oxygen molecules and we say, let's say we have 1 mole of oxygen molecules, that means, sorry, this should be 6.0 not 60.22. We will have 6.22 into 10 to the 23 molecules of oxygen present in 1 mole of oxygen. Similarly, if we have 1 mole of carbon, we will have 6.022 into 10 to the 23 atoms of carbon present within this 1 mole of carbon. And with the definition of mole, we should also define this concept of a molar mass. The molar mass is the mass of 1 mole of substance, and this molar mass is represented in grams per mole. So basically, the molar mass is the mass of 1 mole of either ions, atoms, or molecules of whatever elements we are interested in. And this molar mass is calculated by summing all the atomic masses of all the elements present in a molecule. For example, the molar mass of hydrogen molecule is, first we have to calculate the molecular mass or molecular weight, which is 2 times 1.0 we can the actual atomic mass of hydrogen is 1.008. So the total molar mass is 2 times 1.008 gram per mole. So basically it is similar to molar mass, but the molecular mass, but as we said before, the molecular weight were in atomic mass unit rather than uh, sorry whereas this molar mass is in gram per mole, but if you compare this number, the number here and number in the molar mass will sorry molecular mass will be same, but in term of molar mass this will be is 2.016 gram per mole, whereas molecular weight will be 2.016 AMU. Similarly, if we were to calculate the molar mass of oxygen, we have two within one oxygen molecule we have two oxygen atoms, so 2 times the atomic mass of oxygen is 16, so the molar mass of oxygen is 32 gram per mole. Similarly, if we were to calculate for water molecule, we know that there are two hydrogen atoms within a water molecule, so the atomic mass of hydrogen is atomic mass of all the hydrogen is 2 times 1.008 plus the atomic mass of oxygen is 16, and if we sum all these atomic masses we'll get 18.02 gram per mole. And you can also see more examples of iron and gold in the attached image here. Now let's look at this moles within a chemical equations instead of just chemical formulas. Like we said before, a balanced chemical equations so the mole ratio between reactants and the product. The ratio is given by these coefficients present in the chemical equation. In the reaction here, 2H2 plus O2 produces 2H2O. If we use the molar masses to show how this translates into mass, we can show like this here. In term of mass, we have 2 into each hydrogen molecule has molecular weight of 2.016, and this can be represented as 2 times 2.016 gram of hydrogen, 32 gram of oxygen, 2 into 18.02 gram of will produce 2 into 18.02 gram of water. And if you put these numbers in calculator, this is what we will get. Around 4.03 gram of hydrogen will react with 32 gram of oxygen, and that reaction will produce 36.05 gram of water. And if we look at these numbers, the total mass is conserved, and not just this mass, this equation can also be find the ratio of moles and we can also represent this as, like we said before, 2 moles of H2 reacts with 1 mole of O2 to produce 2 moles of H2. Oh, sorry, this is not H2O2. This is just H2O. Now we can summarize this. Summarize this interpretation of equation. If we are interested in particle level, we will say 2 molecules of hydrogen will react with 1 molecule of oxygen, and that will produce 2 molecules of water. And this form of the chemical interpretation of the chemical reaction describes in describes the equation in terms of individual molecules. And then if we move in the mole level, we can say this equation, from these equations, 2 mole of hydrogen will react with 1 mole of oxygen to produce 2 mole of water. And as we know, each mole represents 6.022 into 10 to the 23 molecules. So if we were to explain this equation in terms of number of molecules, this is 2 times Avogadro's number 2 times Avogadro's number of hydrogen will react with 1 times Avogadro's number times of oxygen to produce 2 times Avogadro's number of hydrogen molecules. And if we were to interpret this equation in terms of mass level, we can convert it into atomic mass and represent in terms of grams to calculate the quantities that we can actually measure in a lab environment. For example, we cannot directly find 1 mole of hydrogen atoms, because we cannot count this many atoms of certain element. Rather, what we can do, we can measure 4.03 gram of certain element. So all this interpretation of chemical equations are important in order to quantify a chemical equation.